Okay, so as I mentioned at the end of my last video, this is kind of my second attempt at teaching Gaussian elimination. Last time I made these videos, I taught a method for Gaussian elimination, and my thought was show students a way that will always work, a very rigid method. First do this, then do this, then do this. And I figured that would make life a little bit easier for everybody. But the problem with doing things so rigidly like that is it makes the numbers not work out real nice, and it kind of ends up being harder than it needs to be. I mean, yeah, there's the advantage of it's always very consistent, but I think in this case the disadvantages outweigh the advantages. And really my big problem with teaching it that way is it's not how I would solve these equations, right? So that just feels a little bit wrong to teach you guys in methods that frankly I would not use. So what I'm going to do in this video is reteach this Gaussian elimination method, which is a really cool method by the way. And I'm going to show you exactly how I would solve this problem. If somebody told me that we had this system of linear equations and two variables that we're trying to solve, and we're trying to solve by Gaussian elimination. We got 2x minus y equals -3, and 3x plus 2y equals 7. The way I would solve it is first, anytime you're doing Gaussian elimination, you have to set up a matrix. And you can't make your matrix until your equations are in this form. Your x's, your y's equal some constant. Fortunately for me, both my equations are already in that form, but if they weren't, instead of saying 2x minus y equals -3, if it said 2x equals y minus 3, I'd want to subtract y from both sides of the equation to get things in this form. Now that I have them in this form, what I want to do is make a matrix from the coefficients, which sounds a lot harder than it is. It's just saying take this 2 equation and don't write the letters or the equal sign, loosely speaking. So instead of 2x minus y equals -3, I'm going to write a 2 for the 2x term, a -1 for the minus y, and a -3 for the -3. And then instead of -3x, I'll write a -3 in this column where my x coefficients go. Instead of the 2y, I'll put a 2 here in this column where my y coefficients go. And then instead of the 7, I'll write a 7 right here. That creates this matrix, which is what I'm going to solve to get my solutions to the system of linear equations. So how do I solve this matrix? Well, there's 3 things that I can do. I can interchange the rows of the matrix, so I could write -3, 2, 7 on top, and 2, -1, -3 on the bottom if I wanted. I can scale a row of the matrix, so instead of writing 2, -1, -3, I could write 4, -2, -6 if I multiply all these numbers by 2, for example. Or I could multiply all these numbers by, I don't know, -10, and I'd get -20, +10, +30. I can interchange rows of the matrix, I can scale a row of the matrix, and I can add and subtract rows in the matrix. So for example, instead of writing this top row, I could write whatever 2 plus -3 is, -1, and then whatever -1 plus 2 is, +1, and then whatever -3 plus 7 is, +4. So those are kind of the 3 tools that I have. Seems important enough that I should write it down over here. So here we go, another arrow on this page that already has tons of different arrows, listing the different tools or abilities, if you want, associated with Gaussian elimination. And it's worth pointing out that this second one and this third one are often used in conjunction. What I mean by that is, instead of just adding the 2 rows together, I might add this row and maybe 5 times this row together. Since I can scale this row and I can add the rows, there's no problem with adding some scalar copy of one of the rows. And I know that all seems really vague and theoretical right now, but trust me, it's not as bad as it seems. One more general theoretical thing that I need to tell you, and then we can actually do this process, which again, it's a pretty cool process. It's worth learning. We have these different tools and abilities, things that we can do to the matrix, but what's our goal? Why would I want to do these things to the matrix? What am I trying to do to the matrix with these tools to get my solution to this system of linear equations? And the answer to that is you want to create what's called a diagonal matrix. And the idea with the diagonal matrix is you have a 1 in the top left corner, and then zeros below it and directly to the right of it, and then another 1 diagonally down to the right of it. And then you'll have some number over in this place and some number over in this place. And when you can rewrite the matrix in this form, the numbers that you see here and here are your solutions to x and y. And you can just sort of memorize that this is the form you want, but really it makes a lot of sense. The idea is, using these abilities, I come up with a matrix that's equivalent to this matrix that I have right here. So if I'm just writing equivalent matrices over and over and over again, and I eventually get it into this form, then think about what this matrix would represent in terms of these equations, right? We went from the equations to the matrix, but if we were going back from the matrix to the equations, if we had 1, 0 number, it would be 1x plus 0y equals some number. And then if we had 0, 1 some number, it'd be 0x plus 1y equals some number. Essentially, it would say x equals something and y equals something. It would be the solutions to the system of linear equations. So let's do it. What you'll want to do first is create this 0 right here. Don't worry about your top left corner being a 1. We can fix that later. But make sure you get a 0 down below that 1. So how am I going to get a 0 here? Well, what I could do is leave my top row completely alone, 2, -1, -3. And then for my bottom row, instead of writing the bottom row, I can write some combination of the top and the bottom row. If I take 3 times the top row and add that to 2 times the bottom row, I'd have 6 plus -6, so I'd get a 0. Not sure you followed that? That's okay, I'm going to do it again. I take 3 times the top row and add 2 times the bottom row. So 3 times -1 is -3, and 2 times 2 is 4, and -3 plus 4 is +1. 3 times the top row is -9, 2 times the bottom row is +14, -9 plus 14 gives me +5. What I did there is I used my second and third abilities together to create a 0 in this position. Now that I've created this 0, I want to move on to this 0. How can I get a 0 in this spot? Well, it's kind of convenient, right? If I added these rows together, it's going to create a 0 in this spot. So I'll leave my bottom row completely alone because I already have my 0 there. And in place of my top row, I'll write the top row plus the bottom row. 2 plus 0 gives me 2. -1 plus 1 gives me the 0 that I was looking for. And -3 plus 5 gives me a 2. Now that I've gotten all the zeros that I need in my matrix, I take care of the ones. I already have a 1 in this position, which is awesome. There's nothing to do in the bottom row. But in the top row, you might notice there's a 2 there, but I need it to be a 1. How can I change this 2 into a 1? Well, it's pretty easy. I can just scale that first row. I can multiply all of the values on that first row by 1/2. If I multiply the values by 1/2, instead of 2, I'd get a 1. Instead of 0, I'd get a 0. Instead of 2, I'd get a 1. And my new matrix would look like this. Often when you're writing your matrices, you put these little brackets on the outside so that people can tell where your matrix starts and where it ends. And that's fine if you want to do that. Although if you space things out sufficiently, you really don't even need those. But the idea is I kind of worked in this L shape. This matrix is equivalent to this matrix, which is equivalent to this one, which is equivalent to the original matrix. But this matrix has the advantage that it immediately tells me that the value of x that I want for my solution is this 1 right here, and the value of y that I want for my solution is this 5 right here. Note that that's the exact same solution that we came up with up here when we did equation addition, and it's the same solution that we got when we used the substitution method. I think the first time students see this Gaussian elimination method, they're like, yeah, I guess it works, but that seems like a lot. I mean, I kind of preferred one of these methods up here. These felt a lot more familiar to me. And that's fine. This matrix method might feel less familiar to you, but this method will actually be more powerful because it'll translate better to harder problems. These problems are relatively easy. I know it's obnoxious when teachers say that, but these systems aren't too bad to solve. But I think what you'll see is when we solve systems of linear equations in 3 variables, sorry, I'll take my dog's toy away in just a sec, it's really hard to do with the substitution method or the equation addition method. But this Gaussian elimination method will work really nicely. So I'd encourage you to learn this method with 2 variables because I think it'll really help you once we get to 3 variables. Let's try another example, actually 2 more examples. If you think you got the hang of it from the first example, you might want to pause and try these on your own, but you might prefer to watch me do one more first. So again, we have a system of linear equations in 2 variables, right? We got x's and y's. And what I want to do is solve that system using this method of Gaussian elimination. So you may recall that the first thing that you have to do is rewrite these equations so they're in the form some number of x plus some number of y equals some number. So I'd rewrite my first equation as 2x plus 5y equals 4. Essentially add 5y to both sides of the equation. And for my second equation, there's a couple different ways I can do it, but one way would be to subtract 6x from both sides of the equation. So I got -6x minus 12y equals -6. These equations produce the matrix 2, 5, 4, -6, -12, -6. This is the matrix that we want to reduce using this method called Gaussian elimination to get our solution. Remember, our first goal is to change this value into a 0. And you can do that with the numbers you see right now, but it's not a horrible idea to reduce the numbers whenever you can. What do I mean by reduce the numbers? You might recognize that all 3 of these numbers are divisible by 6. So before I even try to get a 0 here, I could, if I felt like it, divide all these numbers by 6. It'll keep the numbers a little bit smaller and make things a little bit more manageable. But in the interest of being honest, if I were solving this, I would not divide all these numbers by 6. What I would instead divide all these numbers by is 3. I would make this -2, -4, and -2, because even though I could make these numbers smaller, I kind of don't want to, because my goal is to make this a 0, and with the 2 here and a -2 here, it's really easy to make this a 0. I just add the 2 rows together. So I'd leave my top row completely alone, and then I would sum the rows. 2 plus -2 gives me 0, 5 plus -4 gives me +1, and 4 plus -2 gives me +2. I've created this 0. My next step is to create a 0 up here. How am I going to do that? Well, I'll leave my bottom row completely alone, 0, 1, 2. And then in place of my top row, what I'll do is I'll take the top row and I'll add -5 times the bottom row. In other words, I'll take the top row and subtract 5 times the bottom row. So 5 times this 0 is just 0, and 2 minus 0 is still 2. 5 times this 1 is 5, and 5 minus 5 is 0. And 5 times this 2 is 10, and 4 minus 10 is -6. Good news, we got the zeros in the spots that we want, so now we worry about our 1s. This value is already a 1 coincidentally, so all we got to do is make this value a 1. How are we going to make that value a 1? Just divide everything in this row by 2. We get 1, 0, -3, 0, 1, 2. We have our matrix in the desired form. That means that x is equal to -3 and y is equal to 2 is the solution to this system of linear equations. If you're not sure you did things right, try plugging it in. 2 times -3 equals 4 minus 5 times 2. Let's see, 2 times -3 is -6. 5 times 2 is 10, and 4 minus 10 is also -6. Looks like the first row checks out. What about this second row? Let's see, we got -12y, so -12 times this 2, and that's equal to, question mark in my voice, 6 times x, so 6 times this -3 minus 6 more. -12 times 2, that sounds like -24. 6 times -3, that's -18. Minus 6 more, that's also -24. Cool. It looks like these are solutions to this system of linear equations. And no, you don't need to check your answers at all. It's just so easy to make a little mistake in the arithmetic that it's not a horrible idea to double check if you're worried about it. Let's do one more example, a really ugly example, an example I made as hard as possible in the 2 variable case to see if we've really mastered this method of Gaussian elimination. First, are the equations written in the form we want them in? Well, this first one is, but the second one is not, right? We need the x's to be over on this side of the equation. So I'd rewrite this second equation as -1/3 x plus y equals 5/2. Ugh, fractions. This is going to be miserable. It won't be that bad. Let's take this first equation and this last equation and turn them into a matrix. The coefficient on the x is a 3, the coefficient on the y is a -1/2, and my constant term is a -3. So my first row is 3, -1/2, -3. Coefficient on the x down here is -1/3. Coefficient on the y is the implied 1. And then my constant term is a 5/2. So the second row of my matrix is -1/3, 1, 5/2. You can start reducing this matrix the way it's written if you want, but I wouldn't recommend it. I think it might make your life easier to scale things. Nobody likes fractions, right? I mean, that's not entirely true, but students generally speaking aren't big fans of fractions. And you're going to be adding up multiples of these rows with fractions. That sounds really hard. Why don't we get rid of all the fractions? Why don't we multiply this top row by 2 to make it 6, -1, -6, and multiply this bottom row by 6 to make this first term -6/3, in other words, -2. To make this second entry 1 times 6 or 6, and make this next one 30 over 2, in other words 15. Yeah, it makes the numbers a little bit bigger, but at least it makes them all integer values, which I think will make life easier. All right, what's next? We're trying to create our zeros. You can create the zeros the way it's written right now, but I think I wouldn't. I think what I would do is interchange the rows. I think I'd make it -2, 6, 15, and then 6, -1, -6. Why would I do that? I don't know, just kind of personal preference. It looks easier to me this way to leave these alone and get rid of these values than it does up here. But I don't even know if that's true. Maybe I shouldn't have done that, but at least I've illustrated that you can do that. Anyways, how would I get a 0 in this spot? Well, I'd leave my first row completely alone, -2, 6, 15. And then to get rid of this 6, I want to take this row and add 3 times this row. 6 plus 3 times -2 will give me the 0 that I want, which goes in this spot right here. 3 times this 6 gives me 18, and -1 plus 18 gives me 17. 3 times this 15 gives me 45, And 45 plus this negative 6 gives me 39. Ugh, ugly numbers. Yeah, this was meant to be a really ugly example. Now I need to get a 0 in this spot. Maybe you can see how hard that's going to be, right? These numbers are getting really big, so it'd be nice if I could reduce this row, but 17 is a prime number, so there's not really anything I can scale this row by to make the numbers smaller and keep them as integers. So I think the arithmetic's just going to kind of suck as we go through here. What you could do is take this bottom row and multiply it by 6, or maybe even negative 6. I think that's what I'm going to do. 17 times 6 is not something I'm thrilled to figure out, but let's see. 10 times 6 is 60, and 7 times 6 is 42. So I get 60 plus 42. I think if I multiply 17 by 6, I get 102. And I'm going to multiply it by negative 6 so that I get negative 102 in this position. And then I'm going to multiply 39 by negative 6, because if I multiply this by negative 6, I have to multiply the entire row by negative 6. 40 times 6 would be 240, but I don't have 40 of these 6s. I only got 39 of them. So I'm 6 short of 240. I guess I have 234, and it should be negative, because really I want 39 times negative 6. You might be wondering why I'm creating these huge numbers. Well, because what I'm going to do next is I'm going to take this top row and I'm going to multiply things by 17. Why 17? Hang on just a minute and you'll see. So 17 times negative 2 gives me negative 34. 17 times 6 is the same as the 6 times 17 that we figured out down here. Since they're both positive this time, it would be positive 102. And then 17 times 15. Let's see, if it was 17 times 30, I'd do 17 times 3 and get 51. And then add on a 0 to get 510. But I don't want 17 times 30. I want 17 times half of 30. So instead of 510, I get half of 510, which is 255. From this matrix to this matrix, the numbers got really large, but I did that for a reason. Now, if I replace the first row with the sum of the first and the second rows, negative 34 plus 0 is negative 34. 102 plus negative 102 is 0. And 255 plus negative 234 is positive 21. I'll leave the bottom row alone because I already have the 0 that I want. 0, negative 102, negative 234. I know the numbers are really ugly, but the worst is behind us. The zeros are the hard part. After you get the zeros, getting the ones are really easy. How do you make a 1 in this place? Just divide everything by negative 34. Negative 34 divided by negative 34 would just be 1. 0 divided by negative 34 would be 0. And 21 divided by negative 34, let's see, a positive number divided by a negative number is negative. And 21 divided by 34 is 21 34ths. Down in the bottom, I'm going to divide everything by negative 102 to make this a 1. 0 divided by negative 102 is 0. Negative 102 divided by negative 102 is 1. And negative 234 divided by negative 102 is positive, because a negative divided by a negative is positive. And I'll just write it as 234 divided by 102. I don't think I can reduce this at all, because only 3 and 7 divide evenly into 21, and neither of those divide evenly into 34. But I can certainly reduce this. For one thing, these are both even numbers. So I cut the top and the bottom in half and get 117 divided by 51. And then there's this cool divisibility by 3 trick, that if the sum of the digits is divisible by 3, the number's divisible by 3. So 5 plus 1 is 6, and 6 is divisible by 3, so 51 is divisible by 3. And 1 plus 1 plus 7 is 9, and 9 is divisible by 3, so 117 is divisible by 3. So I'll divide the top and the bottom by 3. 51 divided by 3 is 17. 117 divided by 3, well, let's see, 120 divided by 3 is 40. But I don't have 120. I'm 3 short of that. So I don't get 40. I only get 39. Anyways, the solutions are that x equals negative 21 34ths and y is equal to 39 17ths. Note that 39 17ths is equivalent to 234 divided by 102, and it would have been totally fine to state your answer for y as that number. And you're like, oh, just when I thought I liked this method, I don't like it anymore. Like, this was terrible. This was terrible because the example was terrible. If you try to solve this equation with the graphing method or with the substitution method or with equation addition, it's going to be ugly no matter what, because of these fractions and the fact that the solutions are so ugly. The purpose of this example was just to show you that this Gaussian elimination method works all the time, even if I don't make a big effort to make the numbers work out really nicely like I did in the red and the blue examples. However, as you probably know, if I'm ever going to test you on this stuff, I'm going to make the numbers work out pretty nicely, because without the help of a calculator, I wouldn't want you to have to do all this arithmetic. The method still works, but the arithmetic is maybe a little bit more than you should be doing in our class without the help of a calculator. So don't expect to see examples like you see in green. Maybe the blue and the red are the more useful examples for our purposes. I'll add some brackets to kind of illustrate my process a little bit more, indicate my final answer, and call this good.